Hello. In addition to my previous videos on solving ordinary differential equations, some of which were non-linear types of ODE, I thought we would try a more sort of mechanics-based, applied mathematics-based question relating to astronomy and cosmology on meteorites. And the following question that we are given is this, and that is a spherical meteorite gains mass in the following two ways. The first way is that mass condenses onto it at a rate proportional to its surface area at any instant, and the gravitational field attracts mass at a rate proportional to the mass of the meteorite at any instant. Now, we're asked two questions. We're asked to find an ordinary differential equation that models a rate of accretion of the meteorite in terms of the meteorite's radius r, and we are asked to solve the ordinary differential equation for r. So bearing in mind the first question, or the first part of the question, we have dm by dt. So that is the rate at which mass changes with respect to time, and that's proportional to the meteorite surface area. Now we know that the area of any spherical object is 4 pi r squared. So this becomes dm by dt, which is proportional to 4 pi r squared. Now, where you have a proportionality sign, you can rewrite the equation as dm by dt equal to, I'll write the proportionality constant as k1 there times r squared. So we've got, we'll call this equation 1. Now, we also, in the second part, we're told that the rate of mass accretion, dm by dt, I should have perhaps called this dm1 and that dm2, but we'll just leave it as it is for now. Now, we're told that the rate of accretion of mass with respect to time is proportional to the mass at any time. So this can be rewritten as dm by dt as being equal to k2m, and we will call that equation 2. Okie doke. Right, let me just move this down a little bit. Now, we know that, because we have to get this in terms of r, the final equation, we know that mass is equal to density times volume. And that comes from the relationship density is equal to mass times volume, which is kilograms per meters cubed. Okay, so we just rearrange that equation to get mass equals rho times v. Now we know what the volume of a sphere is. The volume v is equal to 4/3 pi r cubed. So our mass is equal to 4/3 pi r cubed rho. So we can substitute this. We'll call this equation 3. So we substitute equation 3 into equations 1 and 2. So I'll just scroll up so that you can see those equations again. So we have to substitute what we have for m into that and what we have for m into that. And so we approach this as follows. So we have, in the first case, I'll just write this down again. So we have dm by dt equal to 4 pi K1 R squared and dm by dt equals K2m. Okay, so since m is equal to 4/3 pi r, we'll put the rho there and the r cubed there. So this means if we substitute, and I'm going to do this in two separate parts, if we substitute this relationship in to the first equation and then into the second equation, we get d by dt of 4/3 pi rho r cubed, which is equal to 4 pi k1 r squared on that side, and on this side this equation becomes d by dt of 4/3 pi rho r cubed, and that's equal to k2 times 4/3 pi rho r cubed. It's gone off the edge there a little bit, anyway, doesn't matter. And now we need to differentiate the left-hand side and simplify. So for this equation, let's just extend this central line down here a little bit. There we are. So this differentiates, well, we can take the 4/3 pi rho out of the equation, and then we differentiate with respect to t the r cubed. So we get 3r squared, and then we're left with d by dt, and we have an r there. So that becomes 4 pi rho over 3 times 3r squared times dr by dt, and that is equal to 4 pi k1 r squared. And you can see that if we simplify this, the r squareds cancel, the pi's and the 4's, pi and 4 cancels, and the 3 cancels with the 3, and so we're left with rho dr by dt, which is equal to k1. Now this can be rearranged to give dr by dt is equal to k1 over rho, and we'll just call that a. So let me write that underneath so it's a little bit clearer. dr by dt equals a. So that's part of the question answered. Now here we've got the same as we've got over here. So we've got 4/3 pi rho times the derivative of r cubed, which is 3r squared, and that leaves you with dr by dt there, and that's equal to k2, I'll just leave this in brackets, 4/3 pi rho, just a minute, there we are, pi 4/3 pi rho r cubed there. And you can see that the 4/3 cancels, the pi and the rho cancel, and we're left with the 3 over there, but the r squared cancels with one of the 2 of the r's over there. So we're left with 3 dr by dt is equal to k2r, and I'm going to rearrange this to give dr by dt. Let me just improve that d over there. Right, so left with dr by dt is equal to k2 over 3 times r, and what I'll do is I'll call that k2 over 3 constant b. So we've got dr by dt equals br. Okay, so we have 2 new equations, We call this 4 and 5. And all we do now is, in fact, actually, I'm going to call these constants A1 and A1 there, and I'm going to call that B2. So we now add, so if we add 4 and 5, we get 2 dr by dt, which is equal to A1 plus B1r. Okay? And of course, we can divide both sides by 2. So we've got A1 over 2 plus B1 over 2r, and we don't really want the halves in. It doesn't really matter. They're still constants. So we'll rewrite that as dr by dt equal to just A plus BR. And that is the answer to the first part of our question. And now we have to solve it. So solve equation 6. Okay, so how are we going to do this? Well, we can actually separate the variables. So we separate the variables. Just let me, separate the variables, so we get dr over A plus BR, and we've got dt on the right hand side. We put our integral signs in, and then we can integrate. So now I haven't stated what the initial conditions are because I forgot to put those in, but we'll assume that the meteorite starts with a radius of r0 and goes up to some radius r, but because we can't have a limit as a variable as well, so because we can't have a limit as a variable as well, we'll call this big R, and I'm going to call this, excuse me, there we are, I'm going to call that d tau. Right, okay, and the meteorite starts accreting at t equals 0 and goes up to some time t. Right, so assuming that these limits are correct, which for purposes of this question they are, the meteorite starts out with a radius r0 or r0 at t equals 0, and at some future time t, it grows to a size with radius r. So now we can solve this equation, this integral. So quite simply, if we integrate this, we get log of a plus br, and of course you have to differentiate this part in the denominator so that you get 1 over b, and in fact what I'll do is I'll just put the 1 over b there and put a bracket bracket round that. So we've got the log of A plus BR in there, and we're integrating from R0 to R, and that's equal to the right hand side integrated, which is just tau between the limits of t equals 0 and t, right? I'm just going to multiply both sides by b. So we're left with the log of a plus b r between the limits of r0 and r, and that's equal to b times tau between the limits of 0 and t. It just makes the algebra a little bit easier. I'm sorry if my writing's a little bit scrawly, but anyway, let's crack on with the integral. So we've got, if we put the limits in, we've got log of a, let's make that a little clearer, the log of a plus b small r, that's our variable, there we are, minus log of a plus b r naught, and that is quite simply equal to well, we've got a t here, t minus 0, and we can simplify this. So we've got the log of a plus br divided by a plus br naught, and that's equal to bt, right? Let's just scroll down a bit, and then we can do what you should be familiar with now, and take anti-logarithms of both sides. So we've got a plus b r on this side divided by a plus b r naught, and that's equal to e to the bt. Okie doke. There we are. And I'll just rewrite it again so that we can see what we're doing. So we've got a plus br over a plus br naught, and that's equal to e to the bt, right? So we can cross multiply both sides by this term here, a plus br naught, and so we get a plus br equals, and I'm actually going to multiply it out because it sort of helps to skip a step in simplifying. So we've got a e to the bt plus br naught e to the bt, right? So subtracting this a here, subtracting this a from both sides, we're left with br equals, let me see, a e to the bt, and I'm going to subtract that a from here, and we're still left with that at the far right hand side, br naught e to the bt, and so we can rewrite this as br equals a times, in brackets, e to the bt minus 1 plus br naught e to the bt, and dividing both sides by b, we've got r equals a over b times e to the bt minus 1 plus r naught e to the bt. And we could, of course, rewrite that as R equals R naught e to the beta. It doesn't really matter how you write this, but I just prefer to write it in this form with the R naught there times e to the bt minus 1. There you are. And given certain parameter values for A and B, you can graph this solution, but I'll leave that for you to explore. But I hope that that is helpful to you. It's certainly useful if you are wanting to model the accretion of meteorites, for want of a better word. You know, the way meteorites or even other things grow in size in the cosmos. So, as I said, I hope that's been helpful to you, and I look forward to doing my next video, and I hope that you will tune in to watch that. But I bid you farewell for now, so goodbye and see you soon.